All right, here's our second video on the fundamental theorem of calculus. In this video, I'm just going to do a whole bunch of examples. I think you might like that better than the previous video. I know I'll like making it better than the previous video. The previous video got a little too deep into the theory of this stuff for my liking, but it was intentional. I did that because the whole purpose of learning the fundamental theorem of calculus is the theory behind it. Right? These aren't really practical applications that you'll ever use. They're questions that are very contrived that you're asked just to try to strengthen your understanding of these ideas. So it felt necessary to get into the theory. But for what it's worth, the only things you'll ever be tested on in this class are questions that look like the examples that you'll see on this page. So if you suffered through the last one and got anything out of it, great, and I'll try to make this a little bit easier for you. Here's our first example. It's a pretty standard FTC question. We're defining this function, g of x, to be the definite integral from some constant to the variable x of secant squared t dt, of some function in terms of t. And what we're asked to do is to find g prime of x, is to find the derivative of this function. And spoiler alert, the answer is really, really easy. The answer is almost written right here. All I got to do is change the t here to an x. What I'm saying is my answer will end up being secant squared x. But again, this section's weird in that the goal is less just getting the answer and more understanding or proving, if you want, why that answer is the correct answer. So in that spirit, let's show you how to do these problems. So the idea is, oh, I got a definite integral here. No problem. I'll use the evaluation theorem. All I got to do is find the antiderivative of this function and then evaluate it at these two values and subtract them. So the antiderivative of secant squared t dt is what? The derivative of tangent is secant squared. So the antiderivative of secant squared would just be tangent of t. And so what I want to do is take tangent of t and evaluate it from 49 to x. And that's easy enough. All I got to do is change all the t's into x's and then change all the t's into 49s. And that gets me here. What I've done is I've rewritten this function g of x. G of x is this. What I want is g prime of x. So what I have to do is take the derivative of this expression. Well, that's easy enough. The derivative of a difference in two things is just the difference in the derivative. So take the derivative separately. And this is just a constant. I don't know what number it is. I don't know what the tangent of 49 is, but I do know that it's a number. And the derivative of any constant is just 0. So all I got to do is take the derivative tangent of x. Maybe you remember from Calculus 1 that the derivative tangent of x is secant squared x. Minus 0 if you want for the derivative of tangent of 49. What I'm saying is g prime of x is just secant squared x. So the answer to this question is secant squared x. Yeah, I knew that was the answer from the very start. This feels really stupid. Yeah, I guess. But being able to go through these steps shows your understanding of the evaluation theorem and how to take derivatives. So think about it as they're easy answers, but the answers are just a built-in check. Really what I want out of you are these steps in here. Let's do another one. Here's a problem that at first glance doesn't seem to fit the fundamental theorem of calculus, but you'll see that it still works out. We're defining this function g of x like we always do in terms of the definite integral of some other function whose variable is t. And what we want to do is find the derivative of this function. We want to find g prime of x. You might notice, though, that the x is in the wrong spot. Right down here, the x is up top. Down here, the x is on the bottom. I wonder if that matters. Turns out that it does. It turns out that the answer won't be quite as obvious. The answer won't be 1 over x. It'll be really, really close to 1 over x, but when the x is in the wrong spot, it turns out that that just negates this thing. How would I possibly know that? Well, you don't have to have that memorized, because look, we could still use the evaluation theorem here, right? I can still say that g of x would just be the antiderivative of this, so the natural log of the absolute value of t, evaluated from x up to 23. And I still know how to evaluate this thing, just change all the t's into 23s. So the natural log of the absolute value of 23, and then subtract the natural log of the absolute value of x. So this still evaluates to be equal to this, and now I have another expression for g of x, an expression that I have the ability to take the derivative of. So I can figure out that derivative. I can figure out g prime of x. The natural log of 23, I don't know what it is. You don't know what it is, but your calculator knows what it is. It's some number. And when you take the derivative of that number, regardless of what that number is, since that number is a constant, you just get 0. And from that, you need to subtract the derivative of the natural log of x. Well, the derivative of the natural log of x is just 1 over x. Maybe you recall that from your Calc 1 class. And yeah, I know it says the natural log of the absolute value of x. It still works out. You don't have to worry about that absolute value in here. And so what I end up getting as my answer is negative 1 over x. Not quite what I had here. I guess the takeaway is If these are in the wrong position, that ends up negating this answer. Oh, that's kind of interesting. Not really. Maybe more interesting is that you can use the fundamental theorem of calculus even if the question doesn't appear in the exact form that the fundamental theorem of calculus demonstrates. I'll show you another example. The purpose of this example is twofold. The first is to point out that if somebody messes with the variables for you, it doesn't really matter. The variable here will always match the variable here, which will always match the variable here. And then there'll be some other variable here, which will always match the variable here. And it doesn't really matter if you change the letter that's floating around. The standard is to put a t here and an x here. And so that's what I'll do because I don't really see the point in messing with the variables just to mess with you. But in case the homework ever does, I want to make the point that it's okay even if they're different letters. No big deal. The second thing is this one appears problematic because you do not know the antiderivative of natural log of s. You're like, yeah, I do. It's 1 over s. Nah. That's the derivative of natural log of s. You don't know the antiderivative of natural log of x. We haven't learned that yet. It's pretty challenging. We won't learn that for a couple more sections. Eventually, we'll be able to come up with some function that when we take the derivative of that function, we get the natural log of s as our answer. But you don't know that function right now. Trust me, try it. Try to come up with a function that gives you this as the derivative. You won't come up with it. Therefore, you don't know the antiderivative of this. Well, if I don't know the antiderivative, I can't use the evaluation theorem, right? So therefore, I can't get the answer. Well, one of the applications of the fundamental theorem of calculus is that you don't really even need to know what the antiderivative is. It's okay, there's a way around it. Let me show you the trick. The trick you'll do will be substitution. We're going to get rid of this function here for which we don't know the antiderivative, and we're going to call it something that we do know the antiderivative of. We're just going to call it little f of s in this case because s is my variable. We're going to say let f of s be the natural log of s. Let's do this substitution. If we do that, then h of r is equal to the integral from -3 up to r of f of s ds. Right? If natural log of s is just f of s, I can change this into this. And now it'll turn out that I can find h prime of r. And you're like, well, how is this going to work? Trust me. We can use the evaluation theorem on this thing. Because to use the evaluation theorem, all we need to know is what is the antiderivative of this guy, and then we evaluate it at these 2 points. You're like, problem, I don't know the antiderivative of this. Yeah, you do. It's just capital F of s. Right? If we're just using this generic statement, little f of s, to represent the function, then its antiderivative is capital F of s. It has an antiderivative. We just don't know what it is. Right? We don't know the antiderivative of this, but that's fine. Just use this to represent that thing. We'll want to evaluate this unknown function from -3 to r. And you're like, ooh, I don't feel good about that. I don't know how to evaluate. Yes, you do. All you got to do is change all the variables into r's and then change all the variables into -3s, just like you did in this step. So I'd have capital F of r minus capital F of -3. My function h of r is just equal to this if I'm letting little f of s represent this function natural log of s. And you're like, all right, I still don't quite see what's going on. Help me out here. Well, remember in our next step, after we rewrite the original function, we got to take the derivative because the question is asking us to find h prime of r, not h of r, which is what we wrote here. So find h prime of r. To find h prime of r, I got to take the derivative of this thing. How are you going to take the derivative of this thing? What's the derivative of capital F of r? Well, it's little f of r, right? By definition, right? The antiderivative of little f of s is capital F of s. Similarly, the derivative of capital F of r is just little f of r. What's the derivative of capital F of -3? You're like, ooh, that's going to be really hard. No, it's not. This is a number. I know this is a number because I'm changing all the variables in this unknown function, capital F of r, into -3s. So if they're all -3s, then this whole thing is some number. I don't care what number it is. When I take the derivative of any number, it goes away. And so my answer is that h prime of r is just f of r. And you're like, whoa, f of r, what is that? Well, if f of s is natural log of s, then f of r is the natural log of r, which is the answer we knew we would get from the very start, right? Remember in these problems with the fundamental theorem of calculus, the answer is predictable. If the question has the natural log of s right here, and it wants h prime of r, my answer is going to end up being the natural log of r. Just take this and change the variables so that they match up. I knew that was going to be the answer. I just couldn't show the intermediate steps because I didn't know the antiderivative of natural log of s. whenever you're in a situation where you're given a function that you don't know the antiderivative of, you can get around it with this fancy trick right here. I've got a couple more examples, but I think I like shorter videos more than longer videos. So I'm going to make an examples part 2, and that'll be a new video.